Okay, parallel circuit. So let's take a look at the lab. Just to remind you, we have resistance, and there's this thing called conductance. We talked about resistance and conductance. Resistance is opposition to current flow. Conductance is how easy is it for current to flow through a certain material. And they are the reciprocal of each other. Resistance is 1 over conductance. Conductance is 1 over resistance. Of course, the unit for resistance is the ohm. So what would be the unit for conductance? Well, the way I like to do it is it's 1 over resistance, which is 1 over ohms. If I bring that up, that's ohms to the -1. So inverse ohm, they call it a Siemens. So depending on whose book you pick up, probably you'll see a capital S for units for G for conductance. I like to use this unit right here, the inverse ohm. So I like to use that. Now the reason I'm bringing up conductance is, you know, when you have resistances in parallel, we talked about the total resistance is 1 over each branch resistance. So 1 over R1, 1 over R2, and it just keeps going just like that. Well, this is conductance. 1 over R is conductance. So 1 over the total resistance will be the total conductance. 1 over R1 would be G1. 1 over R2 would be G2. And it'll keep going like that. So often when authors write books and they talk about parallel circuits, they like to show conductance because in a parallel circuit, the sum of the conductance is equal to the total conductance. And they like to do that because this reminds you of a series circuit where you just add up all the resistances to get the total. In a parallel circuit, you add up all the conductances to get the total. So if you look at the bottom of the page 97 on your lab, you'll see that formula. GT is G1 all the way out to however many branch resistances you have. Flip over to the next page 98 at the very top. You'll see this formula. We call it the 1 over R rule. And then go down towards the top, towards the middle, in the box. What is that in that box? What is that a statement of? It says, what is it? Kirchhoff's current law. The sum of all the currents entering a circuit junction is equal to the sum of the currents leaving the circuit junction. So basically what goes into a node has to come out. So Kirchhoff's current law, we've talked about that. There's nothing new there. I think everybody here understands it. If you go down to figure 9.2 on your lab, you'll see now that box is confusing. They have what they have is this. They have connections of wires like this, something like that. Then they have a dot right there showing that there's a connection of wires, a node, that's a node. Then they have I1, I2, I3. I think they got even another one down here. So they have I1, I2, I3, I4. They have those wires labeled that way. And then they're just showing directions. They're showing I1 going in like this. They're showing I2 going in like this. I4 is coming out, and I3 is going out. So what would be the relationship between those currents? How would I write the KCL for it, Kirchhoff's current law equation? What would it look like?
I1 plus I2 equals I3 plus
I1 plus I2. What goes in has got to equal what comes out. Put this on the other side so I'm not out of the camera. So it's got to equal I2 plus I3. So you know Kirchhoff's law. You probably, we didn't state it exactly this way, but what you'll find is there's just a different way to say it no matter whose book you pick up. But basically it means what comes in has to come out, current-wise. Pretty simple.
I4 instead of I2. It's not around I4 instead of I2.
Oh, I meant to write I4. Thank you. I don't really care here, but see, I put this on video on
Yeah,
YouTube,
that's
and then other people start looking at that guy. He can't follow them. They don't know. You YouTube people don't know what time it is and what I've been through this morning. So plus, you're not paying for this anyway. They're not. They don't even go here. They're looking at our videos. They don't even go here. Anyway, so the only thing new here that if you've been reading the book, it may not be new. But look at the formula at the bottom of page 98. There's two of them. And then in the middle, there's one. So let's talk about that. Remember the voltage divider rule? Anybody remember that? The voltage divider rule? Talk about the voltage divider rule. Well, there's a current divider rule. A current divider rule, and that's what those are at the bottom. And you might say, well, why are there so many equations? Well, there's a general current divider rule, which is the one in the middle of the page, the one that says Ix equals Rx over R. I want to put EQ because they got IT. I'll explain that in a minute. Times IT. Let's talk about that. See how they have a. Do I have that backwards? Yeah, I got that flipped. I never used this, by the way. I never ever used this. I had a student, he loved the current divider rule, but I never used it. I just use Ohm's law. So this one I don't carry around with me in my head. So the reason I put REQ is because that RT, a lot of students, when they see that, they add the resistors. And that's not what you do. To get R total in the parallel circuit, what do? Use the reciprocal formula, right? So you might want to write yourself a note. Well, this should let you know you're using the reciprocal formula. If you go by what I said in class, that I use an RT when I'm adding resistors to find the total resistance in series. I use an REQ when I'm using one of those parallel formulas. But you got to use one of the parallel formulas for this one. Whereas on the two at the bottom of page 98, they're adding the totals. They got R1 and R2, they're adding. So that you don't use the reciprocal rules for those. So this is the general voltage current divider rule, and it works for any number of branches. So I can have any number of branches. I take my total resistance. Remember, use the reciprocal formula or one of the other formulas to get your total resistance. You don't add to get the total resistance. You use your parallel formulas. So it's the total resistance over the resistor I want to know the current through times the total current. That'll give you the current through that particular branch. Whereas the ones on the bottom, those are special case formulas. Let me show you how those work. Those only work when you have two branches. So if I have something like this, where I have just two resistors, R1 and R2. And let's say I got to know the total current. Say I know the total current coming in here, so I know IT. Let's say I want to know this current. I want to know that one, I2. What you do is, for this formula, you take the resistor you don't know the current through. So if I want to know the current through this one, R2, I'm going to take R1 and put it in the numerator. Divide that by the total resistance. I mean, I'm adding. I shouldn't say total. It's going to be divided by the sum of R1 plus R2. So here you're adding. That's why it's important to understand you're not adding here. You multiply that fraction by the total current, and that'll give you what you're looking for. So the easy way to remember this is if you can remember this quantity right here, then whatever, I didn't do that right. This should be I2. Whatever subscript is here, the opposite subscript should be here. Okay, so if I'm looking for I1, then this will be a R2. Does that make sense, everybody? So what are we doing in this lab? Well, it's really, really short. I keep saying that. They added figure 9-4 at the very top. That wasn't in the old book, figure 9-4. But you can go ahead and do that. You're going to have two resistors in parallel. They're going to have you put the ohm meter across it, measure the ohmic value of it. Remember, in parallel, the total resistance should be less than the smallest resistance in the parallel circuit. So here in figure 9.4, the 3.3K is the smallest. I would expect the total resistance to be less than 3.3K. If you told me the answer was to 3.3 parallel 4.7, you said, hey, I got the answer, it's 3.6K. I say, nope, you're wrong, it's gotta be less than 3.3. Keep going to the bottom, you'll build figure 9.5. And if you look at look at your data sheet, you'll see there's only a couple measurements you have to make. Data sheet. So in the data sheet, of course, you got table 9.1. You have that in every lab where you measure resistances. Now in table 9.2, make sure you read the procedure. But just in table 9.2, you already have the measured value of R1 on the table above, right? You measured R1 in table 9.1. Whatever value you get for R1, write that value in the leftmost column of table 9.2. Hook up your ohm meter to R1. While your ohm meter is hooked to R1, they want you to hook up R2. And now you're going to have R1 parallel R2. Write that down. And then you're going to add R3. Write that down. Then you're going to add R4. Write that down. What they want you to do is in real time, they want you to see that the more resistors you add, you're going to be looking at your digital multimeter, the more resistors you have in parallel, the smaller your resistors are going to get. They want you to see that. All right, so now you've done that. You got all those resistors in parallel. Basically, when you've done that, if you go back to figure 9-5, you built that circuit. The only thing you don't have, you have all the resistors in parallel. The only thing you don't have is the power supply and the ammeter on there. So you'll hook up your power supply, set it to 12 volts. You'll measure the current, and that's the only measurement you got to make, that current measurement. That's why I say this lab is so short. Once you get that current measurement, if you go back to the data, you'll see that you already got table 9.2 figured out. Table 9.3, they want you to compute I1, I2, I3, and I4. You'll compute that. And then, are we missing the table? I might have.
It has a base special question where what's the total current?
Wait a minute, hold on a second. It should have been another part of this.
I just saw it in the book either.
Oh, they've really changed this. Well, the way it used to be, I don't know what the point of this is. What used to happen is they'd have another table where you'd have to, they had table 9.3, but then they had another table where you compute the current to get it using the current divider rule. You just compare them.
Yeah, 9.3 is just us converted using.
I don't really see where you're doing any calculation. Maybe that's in the questions then. Maybe they moved it to the questions. So that seems almost pointless. You're not doing anything but the data. They have you measure, I feel like something's missing. Why would they have you measure the current if you're not going to do anything with it?
The current divider question was moved to question 5.
Yeah.
Oh, then, okay. Okay. That's why they have you measure the current. Well, this will take you all, what, 10 minutes to do? So, I'll tell you what, I'm going to get those resistors, let you guys do this, and I'm going to go ahead and get that Thevenin circuit out. And if we don't finish the Thevenin, I'll talk about it, because it'll take you just a few minutes to do this. I mean, it's just, you can get this data, we can just move on to Thevenin. And then you can either do the Thevenin today or you can do it next week. It's pretty simple too, okay? So I'm gonna leave the tape rolling. Let me grab the parts. You guys can get started on this. I'll make copies of the Thevenin. Once you guys are kind of close to, you probably will finish near the same time, and we'll talk about the Thevenin. And then I'll leave it up to you if you want to do it today or not. I still think you'll have time to do it. We'll probably be done with this in like 10 minutes. Yes. You left that on.
The camera on?
Yeah.
Yes, you did.
He doesn't want to say anything stupid.
Oh, yeah. There's a spooky ghost.
I just want to talk to you about the other week, and I was like, I haven't played that game in a while. I should play it. Now I'm back to the black hole.
Yeah, I would say I feel bad, but at the same time, I don't feel bad at all.
Because like all my friends would be playing, and I was like, I just don't want to play that game. Then I joined them the other day, and now I'm like only playing that game again.
I played 2 ground games yesterday, and both games my team just sprinted it. I say sprinted out.
I got out of class yesterday, just for some electronics, and I want to open to go buy the support game.
All right, come on, guys, get your equipment. Let's go ahead and knock this out, get this lab, and then we'll go ahead and, I think I'm gonna go ahead and do that family lab, because this is really short. I'll just explain it, and then check on your speed, and I think we'll be all right. So go ahead and get it.
Okay, we got an hour technically. Doesn't as lab, if I remember correctly, seems to be.
Well, he's saying they're both quick.
Well, yeah. If I remember the time in the lab takes no longer than that.
I'll go measure it, and then I'll determine if I need a new one. That's 20K. That's a bit much. Yeah.
Did you guys get your trainers yet that I asked you?
Yeah, you guys got last week?
I did. I ordered one, finally. Expensive.
You don't really even need it for this class.
I need those alligator clips. That's bringing mine.
You just use the machines they have here.
Huh?
You just use the stuff they have here.
What, the dip for the trainers? Oh. I paid for one, I might as well get some use out of it.
Yeah, I'm just a frugal person.
What?
So maybe I'm just frugal. I like saving money, that isn't good mine. Apparently, it's all expensive to do.
That's actually 4.7.
The reason I don't use my book that I use for the faster semesters is because it has all the answers in it. So, sitting there, like, I would legit come to lab and you would just sign it. It's already done.
That's big brain.
I'm not that scary. Keep us aboard. Math out the parallel stuff.
What do you need?
I mean, you could print that out.
What do you need?
I wish we could measure it because it's easier.
For the parallels?
Yeah.
What do you do?
I don't know how to measure it. I didn't think about that.
We don't, he didn't bring us any breadboards.
Oh yeah, he did. They're behind the resistors. I was gonna say, I have a breadboard.
Am I blind?
Very bad.
Yep, I got it. Blind as shit.
Huh?
I didn't see these back here. So I was like, how am I supposed to measure the parallel with a breadboard? And I'm not too bright all the time. That's good.
I was like, do you have brain up the breadboard or something?
So. So I think your first step would be to measure your values of your multimeter. Yeah, keep going. So go to page 99.
And like, I wouldn't know.
So your first step is to go R1 in order to carry all together. Yeah, and then measure
His 40 mastery settings.
And then as we go down, we're gonna keep adding
Which
more.
is the same
Which is
even.
why
I don't know
that
how
makes
many
it
they got banned either.
How many do I have? You know that, you know when you like look at all your champions, you have like the total. I think mine's at like
I think it'd be a thing,
Four.
but do you guys, that would be? Yeah.
4/3.
You can't help being the parent you were born that way.
He has like 40 mastery settings. But he didn't do it. And now like somebody gets their figure just to flex on people. Like he made Aurelian Soul.
Yeah.
Just to flex on people.
I've tried playing around, so I think he's fine. I just don't think he's very good.
Yeah, he was like, he's fun, but he's not good.
I think he's fine, I just think he's also terrible. Ever since they changed him to, where they made his W, or instead of it being a toggle, they made it into just a cast ability. Ever since they did that, he's just been really bad. Which the toggle was hard to balance, so I understand, but.
Yeah.
Once people actually started playing him, people were like, wow, this champion was, which he was over 2. But then they changed him. They thought either this champion is worthless or this champion is OP. Which it wasn't.
Thanks.
What do I know? I'm not a right balancer. I'm pretty sure I'm going to be a riot balance.
Yeah, so. Is what it is.